Hello and welcome to this video on rotational motion. Specifically today we're going to be talking about angular momentum and angular impulse. When we first talked about momentum, we defined it as an object in motion will stay in motion, an object at rest will stay at rest, unless acted on by an outside force, and momentum was the tendency for an object to do that. We didn't delineate much between a point mass, a single point moving, and an object moving. It would have a momentum of P equals m times v. The vector meaning that it mattered the direction of travel. And the change between these two states was your impulse. And again, between the point masses and a solid large object, we didn't delineate much because an object moving, we can treat all of its mass as being at its center of mass, so it would be easy to calculate and do calculations for. So this would have a momentum of 0. This would have a momentum of m times v. And the change between them would be equal to the product of force and time. This is linear. Now let's go ahead and do what we've been doing in every other topic to date. Let's take the variables we have and replace them with their angular equivalents. If we start talking about a circular motion object, we can do the same trick we did with torque. So initially we had P equals mv. We multiply both sides by r. We get the angular momentum for an object moving in a circle, L being the shorthand for angular momentum for a single point moving in a circle. Now, if we want to turn this into angular terms, we can replace V with omega r, which simplifies to I omega, which makes sense. Just like torque is force moving in a circle, and we found that it's equal to rotational mass times our angular acceleration, we find that our angular momentum is equal to rotational mass times angular velocity. And the change in this momentum, this change in angular momentum, delta L, which is analogous to delta P, we'll say, well, F forces in a linear system, torque, or tau, is in a rotational system. So our change in angular momentum will be torque times time. You'll note here that there is no J or symbol for change in angular momentum, and that's because it doesn't come up nearly as much. So we have our two big equations here. But this is for a point mass, a singular point moving in space. What about a larger object? What if we had, say, like a disk? And this disk was rotating. Well, if this was the case, we'd have to take all the individual points around the disk and add their individual masses together and all the radiuses together and do a sum of them. So we'd have a sum, our total angular momentum would be the sum of all the masses, all the radiuses, times that. But we've done this math before. We've seen how this works out, and so we can shortcut it. My angular momentum is I times omega. And that's it. That's angular momentum. All we need to know is the moment of inertia for whatever object we're talking about, and the angular velocity, and we can talk about momentum all over again. There is a small issue. Angular momentum is a vector, so it has to have a direction. What is the direction of angular momentum? Well, one of the best ways to think about this is a fidget spinner. A fidget spinner has a center of mass, it pivots around right here. And if we look at this point on the edge, r away, it has a tangential velocity v and a momentum of p. So its momentum will be this way. Now there will be a change, it'll start rotating, but I can use my right hand rule again and get the total momentum. A common way to write this in higher levels is L equals R cross P, which gives me a vector that is perpendicular to the both of them. If you set up your right hand rule and follow this out, you get that the angular momentum is pointing out of the page, out of the screen towards you. And that is how we talk about it. Much like with torque, how out of the screen would be positive, in the screen would be negative. Counterclockwise rotation will produce positive angular momentum. Clockwise rotation will produce negative angular momentum. And if you use your right hand rule, you'll get the vectors. However, because this point is spinning constantly and we don't have anything standing still, what we typically see is the second right hand rule, the curl rule. In this case, if you take a look at an object that's spinning, which again, this fidget spinner, imagine it's going around in a circle like so. You take your hand and put your palm perpendicular to the object so that it's atop the rotating object, and curl your fingers in the direction it's rotating, like the image has up here. You'll get the direction of the angular momentum. So in this case, if this fidget spinner is pointing to the right, I could put my hand on the screen and curl my fingers in the counterclockwise direction, and I get my thumb pointing out of the screen. Positive angular momentum. Again, L is the letter shorthand we use for angular momentum. So this is straightforward. This is fairly simple. All we need to do is just be able to calculate angular momentum, and then a lot of this previous things we learned and understood about momentum work again. So let's get some practice. You're twirling a 0.10 kilogram pencil about a center axis at a constant speed of 14 rads per second. If the pencil is 1.0 meter long, and we're going to treat it as a thin rod rotating about its axis as the moment of inertia is depicted here. Calculate the angular momentum it would have, calculate the torque it would take to stop the pencil in 0.01 seconds, once a teacher yells at you for twirling, or your parents. And then if you apply the torque to the end of the pencil, at the very tip where you catch it, how much force do you need to apply to stop the pencil? Go ahead, give it a try. Check back after you're done. Okay, if you went through and did the math very carefully, you can plug in your moment of inertia, you can plug in the values into it, and you get a value of 0.00012 kilograms meters squared per second. This is not quite the same as a Newton. Newton would be kilograms meters per second squared. The difference between the two is a very important value difference that you do need to keep delineated between. Finding the torque, well, all we're looking for at that point is the change in angular momentum. We're going from having angular momentum to not. So final minus initial, 0 minus the point 0.00012 divided by the 0.01 gives me a torque of 0.012 meters. And then the final step, torque is related to force by R times F sine theta. So force is at a minimum when the angle is directly perpendicular to the rotating object. So the sine of theta would be sine of 90, which means 1. I go ahead and solve, and I get 0.012 over 0.05, which gives me about 0.23 newtons. Anyways, to summarize, angular momentum is just like regular momentum. It's the angular mass term, which is the moment of inertia, times the angular velocity. We use the letter L as a shorthand for angular momentum. It is a vector value. Positive angular momentum from your point of view would be something rotating clockwise, negative would be something rotating counterclockwise, and the vector that we would get out of it is actually perpendicular to how it's spinning. The change in angular momentum is very similar to the change momentum. The formulas are on the screen. Anyways, thanks for watching. Have a good one.